Hello and welcome. My name is Arthur Drichel and I'm happy to present you our joint work in which we take a first step towards explainable DGA multiclass classification. To get started, let's first take a look at traditional botnet communication. Here, bots have usually two simple approaches to contact their command and control server. They either use fixed IP addresses or fixed domain names. But from the perspective of the botnet herder, these approaches have a major drawback, as they are easy to block for a defender once these values are known. This is why modern botnets rely on domain generation algorithms. A DGA is a pseudo-random algorithm generating a huge amount of domain names, which are then subsequently queried by the bot to eventually contact the command and control server. Typically, the botnet herder registers only a small subset of the generated domain names, and therefore most of the bot's queries result in non-existent domain responses. These NXDs can be analyzed in order to detect DGA activities within networks. However, NXDs are not only generated by DGAs, but also by typing errors, misconfigured software, or by the intentional misuse of the DNS. To separate the benign NXDs from DGA-related domains, several binary machine learning classifiers have been proposed in the past which achieve very high accuracies. Going one step further, it is desirable to not only detect DGA-related domains, but also to identify the DGA that generated a specific domain name in order to enable targeted remediation measures. This multiclass classification task is far more challenging as there are currently more than 92 DGA families known. In the past, several promising machine learning classifiers have been proposed for DGA multiclass classification. However, the proposed state-of-the-art classifiers are based on deep learning models. While these classifiers achieve a very promising performance, deep learning classifiers are often said to lead to less well-explainable predictions compared to feature-based classifiers. The black box nature of deep learning models makes it difficult to evaluate the line of reasoning. The resulting lack of confidence makes the utilization of such models impracticable, especially in the security domain. Thus, in this work, we do a first step towards explainable DGA multiclass classification by proposing EXPLAIN, a feature-based and contextless DGA multiclass classifier based on random forests. We focus on the development of a contextless classifier in which features are extracted solely from a domain name that is to be classified, in order to be less resource-intensive and as privacy-preserving as possible. Our classifier achieves competitive results, is real-time capable, and its predictions are much easier to interpret as they can be traced back to the used features. The source code of EXPLAIN is publicly available on GitLab. The main target user group for our classifier are security operations center analysts and model developers. SOC analysts potentially benefit from the use of EXPLAIN over deep learning approaches when analyzing predictions in search for potential false positives or false negatives. Model developers, on the other hand, heavily profit from the adaptability of our approach. For instance, features can be adjusted or new discriminating features can be engineered in order to enable the correct attribution of newly discovered DGAs. We describe the engineering of our classifiers in detail for the sake of transparency, which is a major requirement for explainability. Here we take a look at the three development steps: feature engineering, feature selection, and hyperparameter optimization. Subsequently, we extensively compare our proposed classifier with 6 state-of-the-art deep learning-based approaches and 5 feature-based approaches which we adapted from binary DGA classification to the multiclass classification task. Thereby, we demonstrate that our classifier is able to achieve results competitive to the currently best-performing deep learning classifiers and is at the same time capable of real-time classification. For the development of our classifier and the subsequent comparative evaluation, we make use of 2 completely disjoint sets, which contain samples from 2 distinct data sources. Our source for malicious domains is the open-source intelligence feed of DGArchive. DGArchive contains approximately 115 million unique domains, which are generated by 92 different DGA families. We obtain benign NXDs from the central DNS resolver of the campus network of RWTH Aachen University. From this source, we obtained a 1-month recording of September 2019, which comprises of approximately 26 million benign NXDs. Let's start with the feature engineering process. In total, we studied 136 contextless features, 42 of which were gathered from related work, and 94 are newly developed through analyzing samples of different DGAs and benign samples. As we target a contextless classifier due to privacy considerations, we only focus on features that can be extracted from a single domain name. We divide the 136 features into 64 linguistic features, 17 structural, and 55 statistical features. Linguistic features analyze the presence or absence of common linguistic patterns. For instance, features of this category evaluate whether a domain name contains digits or compute the vowel ratio. Structural features, on the other hand, investigate structural properties of a domain name, such as the domain length. Statistical features capture statistical properties of a domain name, such as the frequency distribution of certain n-grams or the entropy. Regarding the newly developed features, we introduced, for example, simple features that attempt to distinguish DGA families based on the used suffixes in their generated domains, because different families use different sets of suffixes. Other features try to separate DGA families based on the character distributions, as, for example, word list-based families do have different consonant and vowel distributions in contrast to arithmetic and hex-based families. Additionally, we introduced novel features to discriminate different underlying pseudo-random number generators used by the DGA families for domain generation. Examples and detailed descriptions for all studied features can be found in the source code. After feature engineering, the best combination of features has to be selected. The combination of several features might contain mutual information, which could render single features useless for the classification. These features should be removed, as the extraction from the raw data might require significant processing time, which could have a negative impact on the real-time capability of a classifier. For performing the complex process of feature selection, a multitude of different filtering and ranking techniques have been suggested in the past. We derive in total 4 different feature sets. First, we use recursive feature elimination with either mean decrease in impurity or permutation importance as feature ranking methods. And second, we use the 2 relief-based algorithms, ReliefF and Multisolve, for feature selection. As there is no best selection method, as all techniques have their advantages and disadvantages, we additionally combine all sets into an intersection set by calculating the intersection of all sets, and a union set by taking the union of all sets. Additionally, we remove multicollinear features from the union set by hierarchical clustering of the features' Spearman rank order correlation coefficients, resulting in the union Spearman feature set. Note that 60 out of the 76 features from the union set are newly developed, indicating the need of new features for the DGA multiclass classification task. For more details regarding the feature selection process, we refer to the paper. In the upper part of this table, we display the amount of selected features per individual selection method, as well as the evaluation results obtained by classifying the samples of the development set. In the lower part, we additionally include results of the different feature set combinations, as well as an evaluation using all features for comparison. The best evaluation results are achieved with recursive feature elimination and permutation importance for feature ranking. This is remarkable since only 28 of the 136 features are used. The only feature set which contains less features is the intersection set with 11 features in total. However, the F1 score for this set is the worst. All feature selections, except for ReliefF and the intersection set, improved the classification performance compared to the classifier that uses all features. Since it cannot be ruled out that some feature sets might perform well on the utilized data due to overfitting, we consider for our further development the best individual feature set, RFE-PI, as well as the union and union Spearman feature set combinations. We thus perform individual hyperparameter optimizations for all of these 3 feature selections. Additionally, we consider different architectures for our explain classifier. First, we use the random forest implementation, which is inherently capable of multiclass classification. And secondly, we make use of a combination of multiple 1 versus rest binary classifiers for solving the task of multiclass classification. We discard all 1 versus 1 variants due to their slow classification speed, although their classification performance might be slightly better. In total, we thus perform 6 random searches with 120 random trials each. For all 3 investigated feature sets, we obtained best results using the 1 versus rest implementation. As the 1 versus rest variants require more training and classification time than the plain random forest variants, we thus additionally include the fastest model for our comparative evaluation. Before we come to the results of the comparative evaluation, I will quickly summarize the evaluation setup. Here we created a dataset which contains at most 10,000 random samples for each DGA in DGArchive and 10,000 random benign samples. This results in 91 classes, including the benign class. For evaluation, we perform 5 repetitions of a 5-fold cross-validation. We compare our classifiers with 5 adapted feature-based approaches and 6 state-of-the-art deep learning classifiers. We adapt the feature-based classifier Fancy, which implements a support vector machine, and the random forest classifier with its original features developed for the binary classification task, to a multiclass classifier by reducing the problem of multiclass classification to multiple binary classification problems. While the random forest-based implementation is inherently capable of multi-class classification, the support vector machine approach requires modifications. Here we either use multiple 1 versus 1 or 1 versus rest classifiers. Additionally, to the enabled multi-class random forest model, we also evaluate 1 versus 1 and 1 versus rest variants for the random forest implementation. We also evaluate different types of deep learning-based classifiers, including recurrent, convolutional, and residual neural networks. In the context of DGA multiclass classification, the class imbalance problem was investigated and the depicted class weighting was suggested to improve the overall classification performance. Therefore, we include class weighting into our evaluation. The class weights control the magnitude of the weight updates during the training of a classifier. Gamma is a rebalancing parameter, which denotes how much of the dataset should be rebalanced. We denote the cost-sensitive deep learning classifiers with an ending .mi in the following. Here you can see the summarized results of the comparative evaluation. The ResNet-based approaches achieved the best results. Our explain 1 versus rest union configuration is among our classifiers the best and accomplishes an F1 score of over 78%, where this means it is the next best classifier after the ResNet-based approaches. The adapted feature-based approaches of related work perform poorly. Our best explain configuration is by over 21% in F1 score better than the best fancy-based approach, thus indicating the need for new features for DGA multiclass classification. All deep learning models benefit from class weighting. The NYU model profits the most and improves its F1 score by over 2.6%. An F1 score of 78% might appear rather low, but devices infected with DGA-based malware will typically generate multiple domains per day. Thus, real-world counteractions would not have to be triggered based on a single classification, but rather on the fact that multiple domains were attributed to the same DGA. To better visualize the classification performance and to compare our best classifier with the best classifier proposed in related work, we present a combined confusion matrix here. Surprisingly, both classifiers discriminate most DGA families as well as the benign class equally well. Moreover, several DGA families, which are almost not recognized by our approach, are also not recognized by MResNet-MI. These results indicate that the ResNet-based approach might learn similar features as we have selected for explain. However, 3 DGAs are only detected by MResNet-MI. It might be possible to engineer new discriminating features by investigating the samples of these 3 classes in order to enable the correct detection by our classifier. Lastly, both classifiers tend to attribute samples of related DGA families to a single class. Further, we evaluate the training and classification speed of the classifiers. In this table, you can see the training time per classifier and the required classification time per sample. We acknowledge that the reported times are difficult to compare, as the deep learning classifiers are able to take advantage of GPU processing, while the feature-based approaches are evaluated on CPUs. However, the main goal of the study is to determine whether it is realistic to use the classifiers for real-time classification. Although the hardware components might be scaled, the relative time difference in training classification time allow for a comparison within the group of deep learning classifiers and within the group of feature-based approaches. We ignore the training and classification times for the feature-based fancy approaches as they performed poorly. In order to assess the real-time capability, we measured the average and maximum peak of NXTs generated in the campus network. When performing the simple calculations, it can be seen that all classifiers are real-time capable. We argue that explain 1 versus rest union is still real-time capable, although it only classifies 1,872 samples per second. Because during the whole 1 month recording, the maximum packets per second exceeded only for 4 consecutive seconds the mark of 1,872. Thus, for the live classification of a large university network, explain 1 versus rest union would only delay a few packets for a few seconds within a whole month. In summary, in this work we proposed explain, a feature-based and context-less DGA multiclass classifier. We comparatively evaluated several combinations of feature sets and hyperparameters for our approach against several state-of-the-art classifiers in a unified setting on the same real-world data. Our classifier achieves competitive results, is real-time capable, and its predictions are easier to trace back to features than the predictions made by DGA multiclass classifiers proposed in related work. Furthermore, we released the source code of explain to the general public. Surprisingly, the in-detail comparison between explain and ResNet-MI indicated that the deep learning classifier might learn very similar features as the ones we have selected for our explain classifiers. We intended this work to be a first step towards explainable DGA multiclass classification. Ultimately, this requires a focused comparison of different approaches to DGA multiclass classification with respect to explainability. To this end, competitively performing feature-based and deep learning-based approaches have to be contrasted in future work. Thus, in future work, it is required to compare the level of explainability provided by our approach with different techniques that try to explain the predictions of deep neural networks. Finally, future work could analyze the interpretations of deep learning-based models for correctly classified samples, which, however, are incorrectly classified by our approach. It might be possible to extract used features of deep learning models which enable the correct classification of such samples for our classifier. Thereby, it might be possible to further enhance the performance of our approach. With that, I would like to thank you for your attention.